Band theory has nothing to do with music. Band theory is a more comprehensive model for metallic and covalent solids that came out of molecular orbital theory. So the idea here is that the atomic orbitals of atoms within the crystal combine to form molecular orbitals that are delocalized over the entire crystal. When we combine atomic orbitals, we know we get a bonding orbital and an antibonding orbital. The antibonding orbital is higher in energy, the bonding orbital is lower in energy. We looked at what happens when you take two atoms and make a bond and you make molecular orbitals. If you put 3 atoms, 4 atoms, 5 atoms, the more atoms you put together, the less that there's bonding and antibonding orbitals are split. They become closer in energy. So here is the valence orbital for 1 lithium atom. As we combine 2, 3, 4, we're going to see that the splitting that we get between the bonding and the antibonding is they're going to get closer and closer together. And so if you go to a large number, Avogadro's number perhaps, or something ridiculous like that, what you end up with is a band of empty orbitals, those would be the antibonding orbitals, and a band of occupied orbitals, those are the bonding orbitals. And they're going to be very close in energy. And they're delocalized, that's why we call it a band, because it's like over the whole solid. Electrons in those occupied valence band orbitals are kind of stuck because there's atoms from the next, electrons from the next atom, and it's all just congested. I think of it like a freeway that's got just rush hour traffic on it. It's just a standstill, right? Traffic jam, nothing's moving. You can't move because the car ahead of you isn't moving. The car ahead of you can't move because the car ahead of him isn't moving, etc. So that's the valence band. The conduction band, I'm just going to put that down, it doesn't work anymore. The conduction band is empty. It's like a carpool lane that suddenly appears. There's nobody in there. All you have to do is get into it, and then you can go on your way. So electrons can move from those molecular orbitals in the valence band into the higher energy molecular orbitals in the conduction band. Whether they do that or not depends on what the energy gap is between those two bands. In metals, there's no gap in energy between the valence and conduction bands. All you have to do is move over and you've got a clear shot to wherever you're going. So electrons do that all the time. And metals conduct electricity. They also conduct heat because of this same thing. Because the electrons are free to move, the electrons can actually transport thermal energy throughout the metal. And so that's how they conduct heat as well. So water is a pretty good conductor of heat, but it also has a high specific heat capacity. So it'll absorb a lot of heat without changing its temperature very much. So for a conductor like a metal, there's no gap between the conduction band and the valence band. So electrons very easily move up here and then they can go wherever they want. In a semiconductor, there's a small energy gap here. So have you seen on the highway or the road, sometimes they have these like big bumps, right? They're like half circle. And you can drive over them, but you know it when you drive over them. Like chunk, right? So I think of this semiconductor as there's those big half-circle bumps in the highway. And you can get over that. It's going to take a little effort, and then you can get into that carpool lane and you're off. In an insulator, there's a big energy gap. This is the concrete barrier things. You can't get your car over those. So even though this conduction band is over there, and if you could get there, you could move as fast as you wanted, you're stuck here in the traffic jam. Does that make sense? So in a semiconductor, there's just a little energy gap, and so that's why semiconductors conduct electricity a little bit. Okay, limited conductivity. Yes?
Can't insulators still have electricity pass through them?
Insulators can have electricity pass through them, but generally that requires an extremely high voltage, and it results in the breakdown of the substance. Yeah. Of the insulator, yeah.
So it'd be like a
Because
monster truck.
like pure water doesn't conduct electricity.
I
But if you have a high enough voltage, it can electrolyze the water and the electricity will get through.
looks like having a monster truck as an electron.
Monster truck has an electron.
You just jump that barrier.
Sort of, yeah. Sort of.
If you're like supercharged,
Yeah. So doping. We can adjust the conductivity of semiconductors. This is what makes them so useful in computer chips. There's two types of semiconductors, an N-type and a P-type. And we do this by adding a little bit of a different element into the semiconductor. So an N-type semiconductor, we add something that has extra valence electrons. So if we take silicon, which is a semiconductor, and we put some phosphorus atoms in there, the phosphorus atoms have 5 valence electrons. So now what happens is when they're in there and the atomic orbitals become molecular orbitals, because of the extra electron that the phosphorus atom has, that doesn't fit in the valence band. Those have to go up into the conduction band. And so we have some electrons always in the conduction band, and so it's going to conduct electricity more easily than if we didn't have phosphorus in there. So you can make it more conductive by adding more phosphorus. P-type semiconductors conduct by making holes in the valence band. So that's like the congested freeway, and if you go in and you start just, lifting some cars out, you make a hole, then the car behind it can move up. That makes a hole for the car behind it, and so you could get cars moving that way. This is done by doping it with an element that has fewer valence electrons. So if you put gallium in the silicon, gallium only has 3 electrons. And that results in some holes in the valence band, and that allows the electrons in the valence band to move. So silicon chips have millions of these p-n junctions, and that's way beyond the scope of this class. But this idea of p and n semiconductors is at the heart of all of our electronics.